Hello. These are the notes about reaction rates. They kind of summarize what we've been learning about over the last few days. So first, reaction rates is just how fast or slow a chemical reaction happens. We have fast reactions, we have slow reactions. Kinetics is the study of why some reactions are fast and others are slow. So anytime you see the word kinetics or chemical kinetics, it's talking about the study of rates of reaction. So at the heart of kinetics is this idea of effective collisions. So first of all, for chemicals to actually react with each other, they have to come into contact. And we know that those chemicals are made out of particles. And when they come into contact, they need to collide with each other in an effective way. So in order for these collisions to be effective and have a reaction actually happen, first you need sufficient energy, meaning the particles need to be going fast enough to break the old bonds. In a chemical reaction, you make a new substance, you break the old bonds, and then you make new bonds. So if when the particles collide, they're not moving fast enough to break the old bonds, nothing happens. So besides needing sufficient energy, the particles also have to collide with proper orientation, meaning they have to hit the right way. Now in the simulation yesterday, we could control the angle that they collided with each other. In the real world, we have no control over that. The particles are too tiny and they're always in motion. So it's basically down to random chance. So if you can get the particles moving faster and colliding more often, the odds are that more of those collisions will be with the proper orientation. So just as a demonstration, an example of what proper orientation means. We have a chemical equation here. This is synthesis of hydrogen bromide. So we have hydrogen, the element hydrogen, which is diatomic, and we have the element bromine, which is diatomic. And if they approach each other from this angle, they would just bounce off. Like this would be an ineffective collision. And that's because the atoms, if they're going to break their old bonds, they have to be near their new partners so that they can make the new bonds like right away. Like these atoms they're not stable when they're on their own. They partner up for a reason, for that stability. They need that electron to complete their shell. So instead of coming at each other from this way, from the side, if they both approach each other from this angle, then as this comes in, if it collides with enough energy to break the old bonds, you have the BRs right next to their new partners ready to go. So that when they collide, they can break the bonds between themselves and make new bonds and separate off. And their new partners are like right there ready to go. So in your notes, I give you this diagram, and that's what it's kind of meant to show you. With the proper orientation, the new bonds are right there ready to form at the time that the old bonds break, as long as there's enough energy when they smash together. So anytime we talk about or think about rates of reaction, and we talk about some reactions going faster or slower, when a reaction's going faster, it always means that there's more effective collisions going on. A slower reaction has less effective collisions. Okay, so last but not least, let's relate this back to what we actually see in the lab. So the factors that affect the rate of a reaction, probably the largest effect is temperature. Temperature, the higher the temperature means the faster the particles. And if the particles are going faster, that means A, they have more energy for collisions, but B, it also means that more collisions are going to happen. And the more collisions that happen, the more of a chance that some of them will be effective. So temperature probably has the biggest effect. Surface area has a large effect. The more surfaces there are, the more locations or more places there are for collisions. So if you can increase the surface area, then you will have a faster reaction. Probably the second greatest effect on the rate of reaction is concentration. We haven't talked too much about concentration yet. Concentration is like how strong a chemical is. A lot of chemicals are made by dissolving a substance in water. So the more substance that's dissolved in the water, the higher the concentration. So think about like salt water. A little tiny bit of salt, just it's very unsaturated, that would be low concentration. Whereas if you just dump in piles of salt until it's saturated, that would be high concentration. And so obviously if something is a high concentration, that means there's more particles. It's like in the simulation yesterday, when you went from having just like 10 particles bouncing around to hundreds. That was a higher concentration, and so they couldn't go more than, you know, a little tiny bit before they were crashing into something else. They had no room to move. And so if there's more collisions, that's a faster reaction. A couple other factors that affect the rate. The nature of the reactants. Basically, ionic compounds react faster than covalent. This is because in an ionic compound, the particles, the atoms are just held together using ionic bonds, positive and negative charges, whereas in covalent, they actually have bonds holding them together. And we'll talk more about catalysts in the future. Catalysts are basically chemicals that you can add to a reaction that make it go faster. They provide an alternate reaction pathway. We'll explain what that means. Basically, they provide another way of reacting that takes less energy. So at the same temperature, you can get more reactions. And one of the cool things about catalysts is they're not consumed, they're not used up, so they can be used over and over and over. We'll learn more about those later. So I just give you the notes that was in the other assignment about what it means to increase the surface area, basically breaking it up into pieces. And then the last bit of notes is words that you would see on the regions that are related to the surface area. So like, if you imagine like a piece of metal or something, like if we were to react magnesium metal or zinc metal in acid, which is the lab we would be doing right now if we could be together. We could react like a solid block of zinc, and that would be like the largest piece. It's like a brick. The next size down would be lumps. We could take that brick and break it down into lumps. We could, an even smaller than that, particle than that with more material on the surface would be strips, all the way down to a powder with the smallest particles and the least amount of material on the inside. So yeah. The fastest reaction rate would be down here where there's the most surface area. The smallest pieces have the fastest reaction rate. The largest pieces have the slowest. And that's because more of the material is locked away on the inside, and the particles that want to react with it can't get to the inner ones until they work their way through the outside. If it was all broken up, then they could get into the inside at the same time as the ones on the outside. Okay, that's it. That's the basics for rates of reaction. Good luck.